Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the topic conversion of intermediate products. So, in the previous class we have discussed on the petroleum crude, its properties and characteristics, then how we can produce different liquid products from the petroleum crude in a refinery, and we have seen that different liquid products like naphtha, gasoline, kerosene, ATF and diesel or vacuum residue or atmospheric residue we get. So, these products have different applications and requirement of these products may change from time to time. So, meet the requirement in the market, the refinery needs to convert these products from one form to other form as per the requirement of the market, as well as to maintain the quality of the product and environmental requirement also. So, this conversion processes we will discuss in this class, and the contents are need of conversion of intermediate products, then major conversion routes. There are basically two major routes, one is carbon rejection and another hydrogen addition, and other routes are also we will discuss, that is reforming, isomerization, alkylation, polymerization and blending. The need of the conversion already we have discussed that we need to meet the market requirement. So, one product to other product conversion is necessary, and also to improve the product quality. I will give some examples that how the some specific property of that particular fuel oil or that particular liquid oil can be improved by these conversion methods. And already we have discussed meet the market requirement of different products and then achieve environmental standards. Now, we will discuss the carbon rejection routes, that is basically cracking. It takes place in presence of catalyst or in absence of catalyst. So, the cracking means the application of heat to crack the bigger molecules of hydrocarbons into the smaller parts, smaller ones. So, the liquid fractions or we can get more amount of liquid, lighter liquids, and that is the main objective of the cracking. And if we apply catalyst, then the requirement, the process requirements, the high temperature is reduced to some extent. So, we have two types of cracking, one is thermal cracking, another is catalytic cracking, and the thermal cracking temperature is around say 500 to 700 degree centigrade and pressure is around 70 atmosphere, whereas if we use catalyst then the temperature may be 475 to 530 degree centigrade and pressure requirement is also less, that is 20 atmosphere. If we apply this cracking process maybe in thermal or maybe in catalytic path, so the higher hydrocarbons will be converted to lower one, and the two processes having different mechanism of this conversion. So, one the thermal route that follows the free radical mechanism, whereas the catalytic route follows the carbocation productions or carbonium ion and carbonium ion productions. So, there are two Cr5 plus or Cr3 plus, that is carbonium and carbonium ion respectively. So, the mechanism is different and requirement of energy is also less for the catalytic route, that is why it can take place at lower temperature. Now, we will see the catalytic route, that is fluid catalytic cracking. So, when the catalyst is used in a fluidized bed and then feed is passed through this reactor. So, this is the riser part of the reactor, and this reactor here the catalyst is coming as a recycled. So, this catalyst and the feed is reacting here, and then we are getting the product that side, and this catalyst after use in the reactor is coming to the regeneration part, and then after regeneration it is again recycled. So, this is a closed circuit, and where the catalyst and fuel is coming in contact and giving us the required product. So, this is our one fuel, say, which is having less requirement in market. So, we want to convert into other fuel where we will be having more requirement. So, this is the concept of the process, or this is the descriptions of the FCC process. And now, what can be the feedstock we can use in this process? Different types of feedstocks have been used, like say vacuum gas oil, hydro treated VGO or vacuum gas oil, hydrocracker bottom, then coker gas oil, deasphalted oil, reduced crude oil and vacuum residue. So, any one of these feedstocks can be processed through this, so that we can achieve more valuable products from this. So, what are some examples of these products are, say, dry gas, we can have LPG, we can have light cracked naphtha, we can have heavy cracked naphtha, we can have light cycle oil and clarified oil. So, this naphtha, when the naphtha requirement and LPG requirement is high, in that case we can explain the conversion in terms of this, that feed, how much feed we have taken minus this part, then remaining part is here. So, divided into 100 divided by feed. So, this is the conversion of this process. Now, we will see the typical conditions under which this FCC reaction takes place. So, here if we consider here, so obviously catalyst and feed is coming in contact with it. So, what is the ratio of catalyst and feed I am giving, that is important. What is the temperature we are maintaining here? So, here again riser is there. So, at what temperature the regeneration of the catalyst is taking place, that will also influence the degree of regeneration of the catalyst, as a whole the performance of the process. The what type of feed we are using, that will also influence this one. So, we will see catalyst to oil ratio. There are Indian and foreign units, FCC units are there. So, typical properties are shown here, that is catalyst to oil ratio 7 to 9 for foreign unit and 5 to 9 Indian unit. So, reactor riser temperature, that is 540 and this is 490 to 510. Reactor contact time, that is also very important, that is 1 to 8 second, here 1.5 to 3 second. Feed endpoint, then that means what type of feed we are using, that is 600 to 621, here 540 to 560. Regeneration temperature, that is related with the catalyst, here it is 700 to 750, here 640 to 730, and then carbon on regenerated catalyst. So, what is the extent of the regeneration of the catalyst, that is the indicator of the carbon deposited on it, and then this is for foreign units, this one 0.05 to 0.1 and this is 0.3 to 0.6 or 0.01 to 0.02. Regenerator pressure, that is 1.75 kg per centimeter square, here it is 3 kg per centimeter square. So, these are the comparison of two FCC units which is in India and in foreign. Now, we will see the reaction mechanism and how the cracking takes place when we choose the FCC process. So, in this case there are a number of steps. The first is initiation, the first initiation takes place, then is propagation, then is cracking, and then we go for isomerization and cyclization. So, we will see how the cracking reaction initiates. So, we have one hydrocarbon say, and then we have catalyst. So, protonation can take place with this hydrocarbon. So, one H plus from this is coming here and being added to this CH. So, this CH plus. So, then another process may be possible, this may be catalyst. So, that will take one hydrogen from this. So, R1 CH CH2 CH plus and then we are getting here R2. So, this way hydrogen, that is protonation or hydrogen abstraction takes place, that is the initiation. So, we are getting now the carb cation. So, that carb cation will react with another hydrocarbon and then there will be some hydride transfer. So, this is called propagation step. So, here we had plus charge and another hydrocarbon. So, this charge has shifted here and now we are getting this one and R2 another hydrocarbon and it is this charge is shifted to this one. So, that is why this is called hydride transfer. So, one hydrocarbon to other hydrocarbon it is transferred and then cracking step. So, we are getting this one, this carb cation, there will be some cracking in this chain. So, beta scission it is called. So, beta positions, if we have a positive charge here, so these positions will be cracked. So, we are getting here R3 plus and then CH2 CH and R4. So, this will be there some double bond and then R3 will be separated as R3 plus and then we are getting this other product. So, this is called a cracking step. So, we are getting a smaller hydrocarbon now from a bigger one. So, that is desirable to improve the quality. And now, the carbocations which is produced here, what type of carbocations? So, we are discussing here that this hydrogen transfer takes place from one to other hydrocarbon. So, if it is more stable, the carbocation is more stable. So, this one and this one, out of these two, which one is more stable, this one or this one? This one we have to decide, and if we can decide, then we can predict that this conversion will take place or may not take place. So, it has been seen that if this carb cation is tertiary in nature, it may be in secondary or maybe in primary in nature. So, it is shown that the tertiary has more stability than secondary and then primary. So, that way product nature will also change. Then isomerization may also take place. So, we have one secondary carbonium ion in this case. So, there may be some isomerization. So, this H plus some you see, so R CH2 and C plus CH3 CH3. So, this can also take place, that is called tertiary carbonium ion. So, secondary to tertiary formation can also take place and then cyclization, some cyclization reactions can also take place in this process. So, as shown here, so this is our hydrocarbon. So, this is converted to cyclic form. This is also two hydrocarbons, they can make this one. Okay. So, that way the cyclization reaction can take place, and alkylation, condensation and polymerization can also take place. Alkylation may take place, condensation may take place and polymerization may take place. So, these are the different type of reactions which can take place during FCC process. Now, what are the factors that influence the FCC performance? Already we have mentioned some of those, that is feed rate, those are the independent parameters on which it depends, the feed rate, then recycle ratio, feed preheat, riser top temperature, reactor pressure and fresh catalyst activity, that what is the extent of regeneration of the catalyst, and then fresh catalyst selectivity also, the how selectivity, so that we can get a particular product in higher extent. And some dependent variables are also there, that is regenerator temperature, then catalyst circulation rate, then regenerator airflow, coke on regenerated catalyst and product yield. Now, we will see other type of cracking in which hydrogen is added. So, if we add hydrogen, then we will be getting more liquid and at the same time we will be able to remove some sulfur, nitrogen, etc. So, that is the advantage of this hydrocracking reactions, and we see different types of feeds are also used for this process and different products can also be achieved. So, some examples are straight run gas oil. So, gas oil which is produced directly through the fractionations in atmospheric distillation. So, that can be used. Vacuum gas oil which is obtained from the vacuum distillation column, that can also be used. Cycle oil, coker gas oil, thermally cracked stocks and solvent deasphalted residual oils. So, after solvent deasphalting, then we what liquid we get, that can also be used for hydrocracking, and then straight run naphthas and cracked naphthas. So, those are the feedstocks for this hydrocracking process, and some products are liquefied petroleum gas, LPG, motor gasoline, reformer feeds, ATF, diesel fuels, heating oil, solvent and thinners, lube oil and petrochemical feedstocks. So, once we are getting naphtha, will be the naphtha is converted to petrochemical feedstocks. So, that is the use of this, and we will see the chemistry of this hydrocracking process. So, like FCC process, here also different types of reactions can take place, and obviously hydrogen addition is taking place here. So, we will get some hydrogenolysis. So, we will be adding hydrogen, that hydrogen will break the structure here, say here benzothiophene. So, due to the addition of hydrogen, this structure will be converted to some, this is broken here. So, lysis is taking place. So, there is hydrogenolysis. Due to the addition of hydrogen, we are getting some lysis in the structure of the organic compound, and then similarly quinoline and this one. Then hydrogenation say polyaromatics hydrogenation. So, we have one naphthalene. So, if we add hydrogen, so this unsaturation will be removed. So, in one ring it is shown, and in the second step again both the rings unsaturation is removed. So, that way hydrogenation can take place, or hydro dealkylation can take place. Hydro dealkylation can take place here, say this is one aromatic hydrocarbon, we are adding hydrogen. So, then we are getting hydrogen addition here plus dealkylation, dealkylation also taking place, alkyl group is removed from this ring. So, that this type of reaction can also place. Another example is here, only dealkylation has take place. And then hydrodecyclization. So, if we have this type of compound, if we add hydrogen, then decyclization, this is a cyclic compound, due to this there will be some cracking and then hydrogen addition. So, these two different compounds we are getting here, which is not having cyclic structure. So, here decalin hydrogen, it gives this type. So, these are some typical examples, and numbers of reactions are may be possible during the reaction conditions. And then hydrocracking can take place. So, this is the cracking bigger molecules. So, it is converted to smaller one. Hydroisomerization, some isomerization can also take place. So, this is one hydrocarbon, this can be converted to this one, so isomeric form of it. So, different types of reactions can take place during the hydrocracking process or in the hydrocrackers. So, if we think about the catalyst and their properties, then the catalyst will be having some dual functions. One is cracking, we have to crack it, and another is hydrogenation or dehydrogenations. So, one is cracking, another is hydrogenation and dehydrogenations. These are the basic process which is available during the whole process. That is why the catalyst should have two sides, one will favor the cracking, another will favor the hydrogenation dehydrogenation reactions. So, for the cracking reactions, the active sites is acidic in nature, and say some examples is silica alumina or say crystalline zeolite, modified zeolite along with binder. So, these are the some examples of acidic sites in the catalyst, and there will be some other sites for hydrogenation dehydrogenations, and these sites are basically containing metals, that is noble metals, may be platinum, palladium, or non noble metals like molybdenum and tungsten, or nickel cobalt has also been used to increase this hydrogenation dehydrogenation capacity of the catalyst, and noble metals less than 1%, non noble metals 2 to 8%. So, if we use noble metal, the catalyst will be costly, but obviously noble metal in noble metal using catalyst, the requirement of noble metals is less, but non noble metal requirement is higher than this. For example, 2 to 8% for nickel cobalt and 12 to 30% for molybdenum tungsten oxide. So, to reduce the cost of the catalyst, the non noble metals have been introduced and the noble metals have been replaced by this, although there are some comparison between the performance obviously the noble metals catalyst are more than the non noble metal catalyst. Now, what type of reactions will take place? What will be the product distribution? That will depend upon the extent of this acidic site and this your basic sites of these two catalysts. So, accordingly the product pattern will change, and depending upon the feedstocks also this can be monitored, the active sites, number of active sites can be monitored, and the catalyst can be designed. Some example we will show here. So, this is our desired reactions. We want to hydrocrack naphtha or LPG, naphtha to LPG or gas oil to gasoline. So, this is our say desired reactions, we need to do it. So, our catalyst should have strong acidic site, and then hydrogenation activity is moderate, and then surface area high, porosity low to moderate. But when we go for gas oil to jet fuel and middle distillate conversion, or say gas oil to high viscosity lube oil conversions, then we need moderate acidity and hydrogenation activity is very strong. So, we need to add more hydrogen in this case. So, surface area is high. Similarly, when we go for hydroconversion of non hydrocarbon sulfur and nitrogen, then obviously we do not need that acidic behavior, because our objective is to remove the sulfur and nitrogen. So, not to crack the molecules, may not be the cracking of the molecules may not be that important. So, in that case we are using weak acidity, and then hydrogenation has to be strong, because S and N has to react with the hydrogen to give H2S and NH3. So, that way depending upon the nature of conversions which we are interested to achieve in this process, we can design the catalyst as per our requirement. Now, we will see the process how the hydrocracking can take place. So, here we need hydrogen and we need feedstock, we have to provide temperature and pressure. So, here we are make up hydrogen, we are providing some pressure and fresh feed. So, it is coming here. So, that way it is going and heated, preheated, and it again some heating arrangements, and it is coming to reactor stage 1. So, this is one first reactor for hydrocracking. So, after reactions the product is again here cool down, and then it is coming for pressure release to high pressure separator. So, high pressure separator we are getting some gas. So, it will be coming and again it will be recycled with hydrogen. So, it is going to this loop, and then the liquid part which we are having here, that is going for low pressure flash. Again we are doing reducing the pressure here. So, low pressure flash drum it is coming. So, again we are getting some gas molecules, gas, and remaining part is going there for debutanizer. So, some again some pressure reduction. So, butanizer. So, butane is recovered here, then it is going for different fractionation. So, for fractionation, and in the fractionator we get different products, light naphtha, heavy naphtha, kerosene, gas oil, etc. So, the residual part again it is going and added with make up hydrogen, and it is entering into the after preheating it is entering into the reactor 2. So, second stage conversion we are taking, the objective is to get more liquid conversions, more conversions. So, then it is coming, and from second reactor again it is cooled down, and then high pressure separation. So, then high pressure separations we are making a flask. So, we are getting flash, after flashing pressure reduces. So, then the vapors goes there and it is added with the hydrogen for this recycling of this and helps for further hydrocracking. And then the bottom part of this it is coming and sent to the low pressure flash drum. So, again for the recovery of the gases from it. So, this is the overall flow sheet which is followed to perform the hydrocracking of different products, intermediate products. Now, we will see the operating conditions. These are mainly dependent on feed characteristics and product pattern which we desire that we have already discussed, and some typical example are given here. For a hydrocracker processing VGO to produce maximum middle distillates, the reaction temperature is around 370 to 450 degree centigrade, and reaction pressure is 160 to 200 atmospheric pressure, and LHSV that is 0.6 to 3.0, and what is LHSV? That is the liquid hourly space velocity, which is the ratio of liquid volume flow per hour to catalyst volume. So, fractionating section has operating conditions similar to conventional distillation unit. So, these are some operating conditions. Now, we will see the comparison of FCC and hydrocracking. So, obviously, when we are using hydrogen, we need to provide sufficient pressure for the reaction of hydrogen with the liquid part. So, gas phase and liquid phase reaction. So, we need to increase the high pressure. So, pressure is high here. For FCC we do not need that high pressure. Operating temperature, here it is high, but in this case temperature is relatively less because hydrogen is present there. So, construction cost is moderate for FCC, hydrocracker is high because it requires high pressures. So, cost is also higher. Products olefins is high here, here it is nil. So, olefin will not be available because we are providing hydrogen. So, olefin unsaturations will be removed, and then light naphtha octane number, it is greater than 100, but here we get 78 to 81. So, unsaturation is not there. So, octane number is not much with respect to 100 where we get in FCC, but heavy naphtha octane we are getting 95 to 100, we are 40 to 64, and then distillate cetane index. So, cetane index here it is low and we have 56 to 60, and distillate sulfur content, obviously in this case we will be having moderate to high because sulfur removal does not take place in this case, but here hydrocracking sulfur removal takes place. So, we will be very low sulfur, we will be bottom sulfur content is also very low in this case of hydrocracking. So, that way we can compare the FCC and hydrocracking process. Now, we will see the reforming and isomerization process. So, reforming means reforming will reform some products to other one. So, basically in this case it helps to produce high octane number reformate. So, it helps to produce high octane number reformate and different type of reactions which we get here, that is naphthalene dehydrogenation and then paraffins dehydrocyclization and linear paraffins isomerization and naphthenes isomerizations. So, dehydrogenations and isomerizations are desired reactions, whereas adverse reactions which can take place here, that is hydrocracking, hydrogenolysis, hydrodealkylation and alkylation, transalkylations and coking. So, these are not desired for the reforming, and isomerization is required to produce branch say C5 C6 hydrocarbons, that is gasoline product. So, when we need more gasoline to improve the quality of gasoline, this reactions is preferred. Here also this is also reforming is also preferred to increase the octane number. Then we can add some blending. So, blending is possible. So, that can help to improve the quality of the product as well as to meet the requirement of a specific fractions. So, some example we will show here. So, typical motor gasolines that may consist of straight run naphtha from distillation, atmospheric distillations, the straight run naphtha which we are getting, that plus cracked from FCC crackers which gasoline we are getting. If we can make some proper blend, we may get reformate. Reforming is also giving us gasoline, that part can be blend, alkylate, isomerate and polymerate. So, different reactions can give us some gasoline type product. So, if we can mix it, then ultimately gasoline blend will get, and that may have higher octane number than the straight run gasoline. So, in most cases the components blend non-linearly for a given property. That means, if we mix these different gasoline from different sources, so after the mixing, what will be the property? Normally it is not that linear, it is non-linear, and some correlations are developed to predict what will be the properties of this. Then polymerization and alkylation, another type of reactions which are also used for the conversion of one intermediate product to other form, that is polymerization and alkylation. In polymerization, the light olefins are introduced to combine or polymerize into molecules of 2 to 3 times their original molecular weight. So, smaller molecules are converted to higher one. So, the catalyst employed are acidic, that is phosphoric acids on pellets of Kieselguhr. So, that is used, and we see here it requires high pressure in the order of 30 to 75 bars, and temperature is 175 to 230 degree centigrade. And this polymerization derived gasoline may have higher quality. Some example is shown here. Polymer gasolines derived from propylene and butylene have octane numbers above 90. This alkylation reactions also achieves long chain molecules by combination of two smaller molecules. So, one being an olefin and the other as isoparaffin. So, sulfuric acid can also be used, or hydrofluoric acid can also be used for these reactions. This alkylation, when sulfuric acid is used, that is 98% concentration, and say and the temperature is 2 to 7 degree centigrade. The octane number of these alkylates may be 85 to 95. So, this isopolymerizations, alkylations, all these processes helps to increase the octane number and to give better quality gasoline. So, we have discussed different type of reactions which can take place or which we can use to convert one form of liquid to other one to meet the market requirement as well as to improve the quality of that particular liquid fractions. Thank you very much for your patience.